Okay, so there's two things I wanted to discuss towards the end. In this particular slide, if you recall, we can see the Nuclide stability graph. And most of the time you'll see it like this in textbooks. However, in questions, you'll often see a zoomed in version, which looks more like the one on the left. So as an example, if you try and figure out whereabouts this part comes from on the actual graph, you can sort of see it starts from 80, ends at 92, so it's probably around somewhere here to maybe like here-ish. All right, and then from 200, it's probably on the y-axis here because this is atomic. Sorry, not atomic. This is mass number, and so this looks like it's probably, if we look at the sum, it's probably around here-ish, somewhere in this range, right? So we're probably looking at somewhere around here, right? And that zoomed in gives us this. So what this zoomed in version is trying to show you is the path which the unstable nuclide, which is this guy here, this guy is unstable, takes in a series of decays in order to get to the zone of stability. The zone of stability being this point here, right? So you can see all of these paths eventually lead to this particular point, 82,204, right? So this here is a point on the zone of stability. So it is on the zone of stability, right? And the point I want to make here is that sometimes on some graphs you'll see the y-axis as the number of neutrons, and sometimes you'll see the y-axis as the mass number. And depending on whether the y-axis is the neutrons or the mass number, this will change the shape of your alpha and beta decay paths. So I'll give you an example later, but for now let's just focus on if your y-axis was the mass number. So if your y-axis is the mass number and you have an alpha decay, then you're effectively releasing this thing here, right? So you drop in mass number by 4 and you drop in atomic number by 2. So you can see the red line here represents a drop by 4, right? And a drop by 2, 90 to 88, and this transition is an alpha decay. And then when you have a beta minus decay, you are releasing an electron, right, with mass, we say approximately 0, and we have a -1 charge on it, right? So your atomic number, if you're losing -1, that means you're gaining 1, right? So minus 1 is +1, which is why your beta minus decay moves in the positive direction. But notice that it only moves 1 square from 88 to 89, right? 88 to 89. And no mass number change because obviously the mass of electron is 0 approximately. And so there is no vertical movement, only horizontal movement. So that's if this is a mass number versus atomic number graph. But sometimes what you'll find is maybe the axis is changed. So what if we decide all of a sudden that the axis is now, say for example, I'll just draw a 4 grid box here, or I'll draw a 9 grid box just in case. And what if now your axis is protons and neutrons? And let's just say, actually, instead of 3 boxes, we'll draw 4 boxes. So 1, 2, 3, 4, 1, 2, 3, 4. Okay, so I'll switch color pen. So let's say you now have alpha decay, right? So if you have alpha decay, you're still releasing the helium, right? But the number of neutrons that you drop is 2, and the number of protons you drop is 2. So in that situation, your alpha decay would look like this, right? And if you have a beta decay now, if you have a beta decay, then you are you're turning 1 neutron, right? You're turning 1 neutron into a electron plus a proton, right? So as a result, you lose one neutron, so down by one, but you gain one proton, so across by one. So this would be an alpha decay, whereas this here would be a beta minus decay. So notice how it's not horizontal anymore. The number of neutrons changes, and the number of protons also changes. So you can see here that you have to be sort of careful and read your axes carefully if you're dealing with a mass number y-axis or dealing with a neutron axis, and plot the decay path accordingly, or read the decay path accordingly. So that's the kind of main thing you need to be wary of when you see these types of graphs. Aside from that, most questions tend to give you either this graph, and you have to interpret what the series of decays means to get to the stable nuclide, or they will give you a series of decays and ask you to plot it on the graph. So hopefully that gives you a bit of an idea of this nuclide decay path. Now, the second thing I want to talk about is this slide here, which is around carbon-14 dating. So if you recall earlier in the lesson, we talked about carbon-14 being a unstable isotope, and so as a result, the carbon-14 is going to decay over time. Now, what I want you to keep in mind is that the carbon-14 to carbon-12 ratio in living organisms is a relatively steady state constant value. And the reason is because if you think about, say, for example, an organism, let's say this is the organism, it's going to be constantly breathing in, well, not breathing in, sorry, it will constantly be intaking organic matter, right? So it might be eating leaves, say, for example, or other animals, etc. And so it's going to have some amount of carbon intake. And at the same time, it's going to have some amount of carbon output. So effectively what you get is this constant cycling of carbon. So this is really important, right? There's a cycling of carbon that occurs with organic matter, provided that it is alive. Now, what happens when an organism dies is this cycling stops happening. So whatever carbon and let's represent that in red, whatever carbon that organism dies with is now all the carbon-14 it's ever going to get. And so that carbon-14 is not going to be cycled out, it's going to stay there, and there's going to be some initial carbon-14 to carbon-12 ratio with no more input-output. This is the dead organism. And then over time, of course, because carbon-14 decays, this ratio of carbon-14 to 12 is going to decrease. So this ratio decreases over time. And the amount of decrease is dictated by the decay equation. And that is how we're able to figure out, based on the ratio of carbon-14 to carbon-12, how long ago this carbon-14 to carbon-12 was in fact the same as the atmosphere that was surrounding the organism. So to do that, so now that you sort of have a basic understanding of the premise behind how carbon-14 dating works, you can sort of look at this question here. It says here that carbon-14 to carbon-12 ratio in living organisms is 1.3 times 10 to the power of negative 12. So what that tells you is that at least most organic life and life on Earth that is living in the atmosphere as well, carbon-14 to carbon-12 abundance is on the order of magnitude of 10 to the power of negative 12. And your decay rate is 15 dpm per gram. So we can just use that as the activity, right? So you can think about that as the activity, or the decay rate, is equal to negative 15. And you can just treat it like that. And what we find is that the analysis of the carbon-14 content of samples of wood in his tools gives a decay rate of 8 dpm per gram. So that means at A0, which is initially when this wood is still in a tree, it's negative 15. And then once we find it now at AT time t, where t is the time we're trying to find, it is now only -8, right? So we're making the assumption that the wood that is in his tool is approximately produced at the same time as this man, approximately. Obviously, it's not going to be the same, because the man probably killed the tree and then he died a lot longer after that. But in the span of millions of years, that small amount of time is probably insignificant. So we have this AT to A0 ratio now, and we also know that AT is equal to A0 e to the power of negative lambda t. This is something that we discussed in today's lesson, was decay equation. So as a result, what you're trying to find is your e to the power of negative lambda t, which is AT on A0, and AT on A0 is -8 on -15, which is 8 on 15. And so then you can solve for lambda, which is the decay constant, and that should be negative lambda is ln 2 on t half-life, so it's equal to ln 2 on the half-life from the question. So usually they would give you the half-life of carbon, but in this case, oh yes, here. So the half-life of carbon is 5,730 years. So we know that this is 5,730. Now, in terms of units, you don't need to convert it to seconds, and the reason is because your final answer is going to be the same units as whatever units is your decay constant. So you just have to remember that whatever constant you use here with the decay constant, you have to remember what SI unit you're using. So here I'm going to remember that my decay constant is in years to the power of -1. So this is going to give me, and I'm just going to take a quick peek here. Okay, so 0.693, because I do not have my calculator on me, but 0.693 on 5730, right? So that is my decay constant. Let's just redo this here. This here is my decay constant. I can then substitute that back into my time value here. So I know that e to the power of negative, so what I mean by that is this thing here, right? I figured that out earlier, so I can substitute this value so I'll just say this is 2, this is 1, subs 2 into 1. So I get t is equal to ln 8 on 15, but the negative sign shifted over, so I get 15 on 8, and then divided by this number here, which is 0.693 on 5730, and that should give me my time. Remembering that this time t here is the time at which the activity becomes -8, which is the current time. And obviously, without having a calculator, if you type this into the calculator, you should get 5.2 times 10 to the power of 3 years. So by figuring out what the activity is now compared to what the activity should have been that many years ago, you can figure out, and also knowing the half-life of carbon-14 itself, you can figure out how old this, approximately, this piece of wood is, and by extension figure out how long ago this man was probably, existing. So 5.2 or 5,200 years. Okay, cool. So hopefully that gives you an idea of how carbon-14 dating works, and also how the nuclide decay path works.